All right. So today, by the end of the lesson, you'll be able to describe voltage, resistance, and current, and how to use those in Ohm's law. Um, circuits. How's this different than static electricity? Static electricity, static means stationary. Okay. Um, if electrons do transfer, they happen in surges and bolts and like spurts, like all of a sudden. In circuits, electrons are flowing continually. It's a steady flow. Okay. Um, so, in order to make this light up, what were you going for? What is it that was guiding your thoughts? You needed to do what? Oh, come on. Make your middle school teachers proud. You needed to do what? Create a circuit. Okay. So, if you do a workout circuit, that's like a loop, right? Circuit means so we needed to somehow make a circuit, connect the positive and the negative, and put the light bulb somewhere in the middle. You good with that? Like this did not work, correct? Okay. Um, if you did this, this was a complete circuit, but did your light bulb light up? No, it just made the wire hot. It's killing the battery. Okay. You needed to make a distinction between the side and the tip. Okay. Good with that? So, here's what's going on inside the light bulb. Um, so the side casing is connected to a wire, and that goes to the filament. This is the part on an old school battery that gets hot and eventually white hot. Um, we're changing over to LEDs. We'll talk about those later, this chapter. But does that make sense how that works? Completes the circuit, goes through there. Okay. All right. There are four main players, but we're going to study three of those today. The first one is electric potential difference, aka voltage. We were introduced to that term last chapter. So it looks at the comparison of electron crowdedness from one spot to the next, how motivated how motivated the electrons are to transfer. Okay, if they're like crowded over here and they see a spread like a more spacious part over there, like, oh man, and they're motivated to go over there. Okay, this is voltage. I would really suggest putting the cell phones away. Putting the cell phones away. I did, but I didn't. It was a perfect shot. So I almost hit Aiden. Okay. This is important. This is the motive. Okay. This is what motivates electrons to do what they do. Okay. When in circuits, a popular analogy is to compare it to water flowing in pipes or hoses. Okay. In that analogy, voltage is the pressure, specifically pressure difference. Electric potential is the pressure. Electric potential difference is the difference in pressure. If you had a pipe that had 100 psi over here and had 100 psi over here, which way is the water going to go? Nowhere. It's like, But if you had 100 here and 40 here, then all of a sudden it's like, it's motivated. I'm going to lower pressure, from high pressure to low pressure. Good with that? Okay, that's voltage. It's the difference in pressure. Okay, so what I'm going to show you is kind of like my homebrewed model of how a battery works. This isn't really how a battery works, but it's a good picture. Okay, so we're going to pretend like there's this impenetrable barrier between the positive side and the negative side. On the negative side, and then on the positive side, if you are an electron, where would you rather be? Positive or the negative side? Positive side. Do you see how there's an electric potential difference? There's motivation to be up here. Okay, so that is, yeah. So you're good with that? Okay. And if you gave them a way to do that, they're like, woo, yeah, buddy, I want to be up here. Okay. So in this model, what would be seen as a dead battery? Is everybody okay with C? Okay. Electrons are not consumed. They're not eaten by the light bulb. They're still there. Okay. It would be dead. Okay. So what actually happens in a battery is a chemical reaction that provides electrons, and they want to go to a positively charged chemical, and so that's actually what happens. Honors chemistry, do you guys study like voltaic cells, salt bridge? Okay. Okay. So, skip over that. All right. That's one. Voltage is one. Second one is current. Okay. I don't know. I think we're just running out of letters here, but the variable for current is a capital I. The equation for that is delta Q over delta T. So the units on this, what's the unit for Q? Charge. So the unit is coulomb, and the unit for time is seconds. A coulomb per second is equal to an ampere. Okay, and we call those amps for short. The symbol for that is a capital A. This is different than the amp that you plug in your electric guitar into. That is short for amplifier. Okay, good with that? All right, so what does current measure? Popular misconception is how fast the electrons are flowing. The correct answer is B. Okay, it's not about how fast they're going. So here, what is current? So if this is a wire and you're looking at this three-dimensionally, you have a cross-sectional point here. These are the electrons as they flow through. Okay, and what current looks at is how many are going by this point every second. Okay, so if you were hired by the Department of Transportation to measure the current flow on I-65, you would stand over an overpass and count how many cars, like 1, 2, 1, 2, 3, 1, 1, 2, 3, 4, 1, 2. That would be a current measurement. You're not standing there with a radar gun going, how fast are you going? How many? Okay. Is it possible for fast moving cars to have the same current as slow moving cars? Yeah. 1, 2, 3, bumper to bumper. 1, 2, 3. Going fast. Same current. It's not a measure of speed. Okay. In rivers, they actually measure current in the same way. It's not how fast the water molecules are flowing by, it's how much. It's cubic feet per second, CFS. Okay, good with that? Okay, so not how fast. So how fast do how fast do electrons actually move? So turns out really slow. But how, like when I turn on a light bulb, it like automatically comes on. Okay, so here's the analogy for that. In the springtime, you hook up your hose, you turn it on, does water come out instantaneously? No, you have to wait. You're like, whoa, come on. Okay, now it's going. Now, let's say you turn off your hose, but put your thumb over the end of the other side. Now you turn it back on and take your thumb off. How fast does water come out of the hose? Like instantly, like, whoa, the water molecules are moving the speed of light. No, you just bumped out the next guy. Is everybody okay with that? A wire comes completely filled, pre-filled with electrons. When you turn on the light, they just bump out the next guy. Okay? How fast do they go? They actually go in the realm of millimeters per second. Really slow. You got that? Okay. How we doing? We're kind of like getting this pep session schedule rocking and rolling here. All right. So, electrons are going out of negative through the light bulb and into positive. You okay with that? If there's one thing in physics that I could change, it would be this next point here. If you ask any electrician, hey, what's the direction of current? All of them will tell you current goes out of positive into negative. In the opposite direction the electrons are flowing. And so you ask why? Well, the reason is because that's the way we've always done it. And we've never changed. So, some history. Ben Franklin was like one of the founding fathers of this idea of electricity and like how this works. And he hypothesized that there were charged particles that you couldn't see and they were flowing. And he was an optimist and like positive things are flowing. And he did a whole bunch of science to like verify. And you're like, yep, this model of flowing charges works great. And people built on top of that. And later, they're like, oh, those are electrons flowing, and those are negatively charged. Huh. Well, we've had decades of this science that works out fine. Why should we change? We'll just keep on going. We'll just assume that positive things are flowing, even though negative things are the things flowing. There's nothing's flowing in the direction of the red arrows. There's only things flowing in the direction of the green arrows. So about 10 years ago, I was like, oh, we're gonna start at the grassroots. We're gonna overthrow this stupidness. And kids would come back after college like, Smiley, my professors like laughed at me, like current goes out of positive into negative. So here's where I'm landing. Know that the green is actually what happens, but know that everybody talks in the red. Okay? So if I ask you, hey, which way is current going? You're going to tell me the red out of positive into negative. If I ask you which way is the electrons flowing, you're going to tell me the green going out of negative into positive. Sorry, that's just the world we live in. Can't. Tried to fix it. Someone more important than me needs to fix that. Yep. Sorry. All right. Depending on what I ask you. If I say current, what's the direction of current? It's the red. If I say direction of electron flow, you say the green. All right. Everybody good? Got a guess? All right. This is the red out of current is out of positive into negative, counterclockwise. Good? All right. Third player is resistance. Resistance has a capital R. The unit of resistance is an ohm. This one's fun. The abbreviation is a capital omega. Okay, that's going to take a little bit of practice to write. All right, so resistances, this has to do with like insulators and conductors. It's not like a insulator bucket and a conductor bucket. So this is like, it's more of a spectrum. Okay, like gold has less resistance than copper. So copper would be a better, has more resistance than gold. It's like, it's a spectrum. Okay. But insulators have high resistance, conductors have low resistance. Good? All right. When you if you've ever seen a circuit diagram or like circuit plans, okay, these are called schematic diagrams, and we have some symbols that represent different things. So this would represent a battery. Okay, a long line and a short line parallel to each other. The long side is positive, the short side is negative. Here's how I remember that. The negative sign is just one stick. Positive sign is two sticks. You do that. So that's a battery. Things that are, wires are usually drawn at right angles to each other. Okay, these are wires, and then when you get to the light bulb, this is the resistor. drawn as kinks in a hose. Okay, so that would be a schematic diagram.
I'm paying attention the whole time.
Multitasking is a myth. Okay, good with that? Okay. Ohm's law. This is as important and as useful and will be used as F equals MA was last semester. Okay. Ohm's law. Voltage is equal to current times resistance. Okay. Mathematically, that's the easiest way to write that. Conceptually, you can write that like this. Okay, voltage over resistance. So, to look at the roles things play, voltage, this motivates electron flow. It's the push, it's the pressure, like, come on, let's go. This is resistance resists electron flow. Okay, do you see the conflict of interests? Do you see the battle? Okay, the result of that battle is current, the flow of electrons. Okay, so voltage is like, come on, let's go. Resistance is like, whoa. And that ratio, voltage to resistance, that determines how much current there is. Okay, so how can we make current go up? Tell your neighbor. How could you make current go up? Okay, so you could either increase the voltage or decrease the current. Good with that? All right, so we will use Ohm's law a lot. Okay, the difference between current and voltage. All right, so voltage has, because we use it in life, you've heard of it outside of science class, you usually have some wrong ideas. So voltage is the push, is like pressure difference. Okay, it does not flow. Voltage does not flow. Okay, it just pushes. Okay, current, this is the flow. The current flows. Okay, the prepositions that we use, this is, this goes through stuff. Current flows through something. Voltage is measured across something. It's like how much pressure difference is there from 100 psi across to 40 psi. Pressure difference across these 2 points would be 60. Good with that? Tell your neighbor. Correct answer is okay. The voltage, the push, enables the current to happen. Cause and effect. Okay. All right. So, not to muddy the waters, but we have a lot of different names for electric potential difference or voltage. You could have, there's certain parts of a circuit that take energy away. So voltage looks at how much energy there is per coulomb is being transferred or being converted. Which part of the circuit uses or takes energy away, takes electric potential energy away? The battery, the wires, or the light bulb? You think that takes electric potential energy and converts it into another type of energy? Between C and B, the light bulb. Does that make sense? It takes that electric energy and it converts it to heat and light. Okay. In that circuit, there's another part that gives energy. It's a circuit. It's a whole cycle. So what part of this circuit gives energy to the electrons? The battery, the wire, or light bulb? Battery is the source. Okay. This would be known as a potential gain or a voltage gain across that. Okay. It's what giving. It's the thing that pressurizes it. Okay. Good with that. Some people liken a battery to like a pump in the water flow analogy. Okay. So voltage gain. All right. In this simple circuit, rank the current at the different points. Thumbs up when you have a guess. Correct answer is probably not what you think. The correct answer is D. Okay. Here's why. Current at all points of a river are the same. Okay. It's not how fast it's going. It's how much water is going by a certain point every second. Okay. In a river, if there was more water coming in than going out, you'd get flooding. If there was more water going out than coming in, you'd get this like what happened to the water? Okay. All the water that goes in goes out. You get different speeds because, like, if you think about your canoeing trips, it's more rapid when the river is shallow. It's slower when the river is deep. You have the same amount of water going by that point, any point every second. You good with that? Okay. Whew, made it. Good job. You have a worksheet to do on Monday. I know I'm giving you homework over the weekend. Apologize. It is a simple worksheet. Like, that is an easy 10 points in the bag. I know. It isn't. Don't forget.